Look up tonight and you will see a sky that should not be empty. Our galaxy holds hundreds of billions of stars, and many burned for billions of years before our sun. By every reasonable estimate, someone should have crossed it, colonized it, or at least left a single detectable whisper behind. Instead, there is only silence, not quiet, silence. And there's a name for what that silence might mean, an idea so unsettling that some scientists hope it is wrong. It suggests that every road from lifeless rock to a long thriving spacefaring civilization passes through a door almost nothing survives. The terrifying question is not whether that door exists. It is whether humanity has already walked through it or is standing in front of it right now. Before we go further, a small and honest ask. If questions like this are the kind you like to sit with, consider giving this a like and subscribing. It helps more than you would think, and it quietly tells me to keep making these. No pressure, no hard sell, just settle in, get comfortable, and let us think this through together. Are you comfortable? Now, let's begin. Imagine someone hands you a single grain of sand and tells you it represents our sun. Now picture every other grain of sand, on every beach, in every desert, across the entire surface of the Earth. That is not a flourish invented for effect. It is the conservative way to describe the number of stars in the galaxy we happen to live inside. The Milky Way stretches roughly 100,000 light years from one edge to the other. That means light itself, the fastest thing that exists, traveling at about 300,000 kilometers every second, needs 100,000 years just to cross from one side to the far side. And packed into that vast spinning disk are at least 100 billion stars, with many careful estimates pushing the real figure to 2, 3, even 4 times that number. Now hold that scale in your mind and add a second ingredient, because size alone is not what makes this story unsettling. The second ingredient is time. The Milky Way is old. Not old in the way a human being or even a mountain range is old. The galaxy has been assembling stars for somewhere around 13 billion years. Our own star, the Sun, did not ignite until roughly 4.5 billion years ago. Do the simple subtraction and a staggering fact falls out of it. For something like 8 billion years, the galaxy was already building stars, forging planets, and cooking the basic chemistry of worlds long before Earth was anything more than a possibility. 8 billion years of a head start that had nothing to do with us. Let that number breathe for a moment. Human civilization, the kind with cities and writing and agriculture, has existed for roughly 10,000 years. The technology that could announce our presence across space, radio, has existed for barely more than 100 years. Against the 13 billion year span of the galaxy, our entire technological era is a single flicker, like a newborn opening its eyes for the very first time and assuming the room must always have been empty because no one happens to be speaking in the half second it has been awake. We are not the seasoned residents of this galaxy. We're the latest arrivals, and almost everyone who could have come before us had an enormous amount of time to do so. And that point about being latecomers deserves to be sharpened, because it is easy to let it slide past as a poetic flourish when it is actually a hard, uncomfortable piece of arithmetic. Picture the timeline of the galaxy laid out as a long road, and scatter along it every moment a rocky, Earth-like world cooled and steadied enough to begin its own slow climb toward complexity. On that road, the Earth does not sit near the front. It sits far down toward the recent end. Billions of suitable worlds had their water and their warmth and their stable orbits in place 1 billion, 2 billion, 4 billion years before ours did. So here is the squeeze. If the climb from lifeless rock to a visible civilization is the kind of thing that can be done at all, then somebody, somewhere, almost certainly reached the top long before humanity took its first upright step. We would not be the pioneers planting the first flag. We would be among the last to arrive at a party that should already be in full swing, walking into a hall that countless others entered ages ago. And the hall is empty. That is not a comfortable thing to sit with. Either the climb is far harder than it looks, or something is removing the climbers, because by every fair reading of the timeline, we should be the newcomers, not the only ones. Here is where the head start becomes genuinely strange. Consider what humanity accomplished in just the last few centuries. We went from sailing ships to spacecraft, from candle flames to lasers, from shouting across a field to flinging signals across the solar system at the speed of light. Now take that rate of change and stretch it not across centuries, but across 1 million years, which is still a tiny sliver of the galaxy's lifetime. A civilization with that kind of head start would not merely be more advanced than us, it would be unrecognizable. It would have had time to spread, to build, to leave fingerprints across thousands of star systems. And 1 million years, remember, is almost nothing here. You could fit that span into the history of the Milky Way more than 10,000 times over. This is the exact thought that stopped a brilliant man cold in the summer of 1950. The physicist Enrico Fermi was at the Los Alamos laboratory, walking to lunch with colleagues. The conversation had drifted, as lunchtime conversations do, toward a lighter subject. The flying saucer reports that were filling newspapers at the time. There were jokes. There was laughter. And then, in the middle of the meal, after the subject had already moved on, Fermi reportedly looked up and asked a question that has haunted science ever since. Where is everybody? His colleagues understood instantly what he meant, because Fermi was not asking about sources. He was running the numbers in his head, the same numbers we just ran. The galaxy is enormous. The galaxy is ancient. The opportunities for life to arise and spread have been almost limitless. So, given all of that, why is there no sign of anyone at all? That casual lunchtime question became one of the deepest unsolved problems in all of science, and it carries a name that matters. We call it the Fermi Paradox. Pay close attention to that second word, because people misuse it constantly. A paradox is not a mystery. A mystery is simply something we do not yet know. A paradox is a contradiction. Two things that both appear to be true, but cannot both be true at the same time. On one side, our best reasoning about the size of the galaxy, the abundance of stars, the availability of planets, and the depth of cosmic time says the galaxy should be teeming with civilizations, or at least littered with their leftovers. On the other side stands the actual evidence, which shows us nothing. No signals, no probes, no structures, no ruins on any world we have examined. Both of those cannot be correct, and the gap between them is the paradox. And notice something important about the shape of this problem. It is easy to explain why one civilization might never appear or might quietly die. Bad luck. A wandering asteroid. A planet that never quite reached the right conditions. That kind of explanation is cheap and obvious, But the Fermi Paradox is not asking about one civilization. It is asking about all of them, across billions of years, across hundreds of billions of stars. For the galaxy to be this silent, the explanation cannot be a single piece of bad luck somewhere. It has to be something that applies almost everywhere, to almost everyone, almost every time. That is a very different and far heavier requirement. To feel the full weight of it, you need to understand a concept that astronomers call the colonization timescale, because this is the detail that turns a curiosity into something closer to alarm. The argument goes like this: suppose a single civilization, anywhere in the galaxy's long history, decided to expand. They would not need faster than light travel. They would not need anything magical. They would only need ships that travel at a modest fraction of the speed of light, settle a nearby system, and over a few thousand years build new ships that move on to the next one. Slow, patient, generation after generation. When you actually do the mathematics of that spreading wave, the result is shocking. Even at that unhurried pace, a single expanding civilization could reach across the entire Milky Way in something like a few million to a few tens of millions of years. Sit with that, because it is the heart of the contradiction. A few million years sounds enormous to a human being, but it is a rounding error against the age of the galaxy. The Milky Way has had room for that colonization process to run not once, not twice, but thousands of times over. So we are not asking the gentle question of why we have not yet bumped into a neighbor. We are asking the far more disturbing question of why, after billions of years and thousands of available colonization windows, the galaxy looks completely untouched. One civilization, at any point in the deep past, choosing to expand, should have been enough to leave traces everywhere, including here. And yet, here is empty of any such trace. For a long time, someone defending the optimistic view could simply say the ingredients for life are probably rare, and that would have quietly dissolved much of the tension. Maybe planets themselves were uncommon. Maybe Earth was a freak, a 1 in a billion arrangement that almost never repeats. For most of human history, that was a perfectly respectable position because we genuinely did not know how common planets were. We had exactly one example of a planetary system, our own, and you cannot build statistics from a single case. That excuse, that comfortable escape hatch, has now been slammed shut, and the instrument that closed it was a space telescope named Kepler. The Kepler mission did something deceptively simple and profoundly important. It stared at a single patch of sky containing thousands upon thousands of stars and watched with extraordinary patience for the tiny, repeating dips in brightness that happen when a planet passes in front of its star. And what it found rewrote our sense of the galaxy. Planets are not rare. Planets are not special. Planets are everywhere. The data points to a galaxy where, on average, essentially every star hosts at least one planet, and many host several. That means the raw count of planets in the Milky Way is not in the millions or the billions. It is in the hundreds of billions, very likely in the trillions. The cosmic shelves are absolutely stocked with worlds. And there is a detail in that discovery that sharpens the problem rather than softening it. A detail about what kind of star is most common. When we picture another sun, we tend to imagine something like our own, a bright yellow star. But our sun is not typical. By far the most numerous stars in the galaxy are the small, cool, dim ones, the class astronomers call Type M, the red dwarfs. They make up something like 3/4 of all the stars that exist. And here's why that matters. These little stars are extraordinarily long-lived. Where a star like ours burns for roughly 10 billion years, a red dwarf can shine steadily for tens or even hundreds of billions of years, far longer than the universe has so far existed. If life needs time, then these patient, frugal stars offer it in almost unlimited supply, and there are billions upon billions of them, each potentially hosting worlds, each burning calmly for spans that dwarf the entire history of our own sun. The galaxy is not only stocked with planets, it is stocked with planets around stars that will keep their hearths lit almost forever. Of course, not every planet is a candidate for life. We care most about the ones that sit in the habitable zone, the band of distance around a star where temperatures could allow liquid water to exist on a surface. So astronomers narrowed the question: of all those countless worlds, how many are roughly Earth-sized and orbit in that temperate region? The estimates carry real uncertainty, and honest scientists argue about the exact figure, but the conservative answer is still breathtaking. The number of potentially habitable, roughly rocky worlds in our galaxy alone is most likely in the billions. Billions of places where, at least in principle, the basic conditions for life as we understand it could be available. The galaxy is not a barren desert with one improbable oasis. It is, by every measurement we now have, soaked in real estate. Now, a careful skeptic might push back here and say that not every corner of the galaxy is equally welcoming, and that is a fair point, one worth taking seriously rather than waving away. There is an idea astronomers call the galactic habitable zone, the notion that calm, life-friendly real estate is not spread evenly across the whole disk. Too close to the crowded, violent center of the galaxy, and the neighborhood is bathed in radiation, raked by exploding stars, and stirred by the gravity of passing suns that could fling a planet's orbit into chaos. Too far out toward the thin edges, and there may not be enough of the heavier elements that rocky planets are built from in the first place. Somewhere in between lies a more peaceful band, a ring of relative quiet where worlds can sit undisturbed for the billions of years that everything else seems to require. But notice what this does, and does not rescue. Even if you shrink the welcoming territory down to that calmer band, you are still left with tens of billions of suitable stars within it. Trimming the galaxy's good real estate does not empty it. It only reduces an unimaginable abundance to a merely staggering one. The expectation that someone should be out there does not go away. It barely flinches. And here is the detail that twists the knife, because some people will immediately object that interstellar distances are simply too vast. That even if life is common, nothing could ever cross the emptiness between the stars. So, of course, it all stays isolated and silent. That objection sounds reasonable until you look at what has been drifting through our own solar system. In recent years, we have caught direct, confirmed proof that material does cross those distances. Objects from other star systems pass through our neighborhood, and we have now watched several of them do it. The most striking recent example arrived in the summer of 2025. On the first day of July that year, a survey of the sky run by the Atlas network of telescopes spotted a faint moving point of light. Within days, astronomers measuring its path realized this was no ordinary comet. Its orbit was not a closed loop around the sun. It was a wide-open hyperbola, the signature of something that came from outside our solar system entirely, fell inward, and would leave again, never to return. They named it 3I Atlas, marking it as only the third confirmed interstellar object we have ever caught in the act. The first was the strange tumbling sliver we called Oumuamua, seen in 2017. The second was the more comet-like visitor named Borisov in 2019. 3. I-Atlas was the third, and it was moving astonishingly fast, sweeping toward its closest approach to the sun in late October at tens of kilometers every single second. What makes 3I Atlas so relevant to our story is not just that it came from somewhere else, it is what the careful study of it revealed. As telescopes, including the most powerful one we have ever launched, turned to examine its glowing envelope of gas and dust, they measured a chemical fingerprint unlike the comets born in our own system. Its coma showed an unusual abundance of carbon dioxide relative to water, and a striking poverty of certain carbon-bearing molecules. Working backward from that chemistry, researchers concluded that this object likely formed around another star a very long time ago, in conditions different from our own, and was then flung out into the dark to wander between the stars for an immense span of time before crossing our path by pure chance. Think carefully about what that confirms. It tells us that planetary systems do not stay sealed. They build worlds, and in the violent process of building them, they hurl debris, ice, and rock out into interstellar space. That material genuinely travels. It crosses the supposedly impassable gulf between stars and arrives, intact, in other systems. The galaxy is not a collection of perfectly isolated islands with nothing moving between them. It is connected. Pieces of distant alien worlds physically reach us, and pieces of our world have surely been flung out to reach others. If frozen chunks of other star systems can complete the journey, then the old comfort that distance alone guarantees eternal silence simply does not hold. For decades, scientists have tried to organize this tangle of expectation into something they could actually reason about, and the most famous attempt is the Drake equation. It was written down in 1961 by the astronomer Frank Drake, and it was never meant to spit out a precise answer. It was a way of breaking one impossible question into 7 smaller, more honest ones. Walk through them slowly, because the chain is the whole point. You start with how many suitable stars there are. Then you ask what fraction have planets, and we have already seen the answer, nearly all of them. Then, of those planets, how many could in principle support life? And again, the answer runs to billions. So far, every term we can actually measure comes back large and generous. Then, the chain reaches the terms we cannot yet measure, and this is where the honesty bites. What fraction of suitable worlds actually see life begin? On how many does that life become intelligent? On how many does intelligence build a technology that radiates into space? And finally, the cruelest term of all, how long does such a civilization last before it falls quiet? Multiply the 7 together and you get a rough estimate of how many detectable civilizations should be broadcasting right now. The unsettling thing about the Drake equation is what happens when you feed it numbers. The early terms, the ones about stars and planets, we now know fairly well, and they are large. The galaxy is full of stars. Those stars have planets. Many of those planets could, in theory, host life. Plug in even cautious values for this parts, and the equation keeps pointing toward the same stubborn conclusion. There should be others. The optimistic case is not built on wishful thinking. It is built on the parts of the equation we have actually measured. And those measured parts say the sky should not be empty. The only way to drive the final countdown to 1, down to us alone, is to make one of those last unmeasured terms almost impossibly small. Hold that thought, because it will become the entire story. Which brings us face to face with the silence itself, and it is worth being precise about how thorough that silence has been. Because the easy dismissal is to say, we have barely looked. There is real truth to that. The honest scale of our search is humbling. We have listened seriously for only a few decades, with instruments pointed at a modest number of nearby stars, scanning a narrow slice of the possible frequencies for relatively brief windows of time. Even the most ambitious modern effort, a project devoted entirely to listening across the sky, has examined only a thin sample of the galaxy's hundreds of billions of stars. If a civilization were broadcasting on a frequency we have not checked, in a direction we have not pointed, during years we were not listening, we would have missed it completely. So part of the silence is simply that we have not yet searched enough of the haystack to be sure there is no needle. But notice what the silence still includes, because there are things our crude searches should have been able to catch. Things that do not require us to be listening on exactly the right channel at exactly the right moment. Imagine a civilization that had spread and grown for 1,000,000 years, a span that is nothing on the galactic clock. Such a civilization would be hungry for energy on a scale we can barely picture. One famous idea imagines them building structures around their own star, swarms of collectors that drink in its light to power everything they do. And here is the thing about energy. It cannot simply be used and then vanish. The laws of physics demand that whatever they harvested would eventually be radiated back out as waste heat. A telltale glow at the longer, redder wavelengths of infrared light. A star wrapped in machinery would look strange, dimmed in visible light but blazing in heat. A fingerprint no natural object easily mimics. And astronomers have actually gone looking for exactly that, sweeping across enormous numbers of stars and even whole galaxies, hunting for the infrared signature of a civilization feeding on its sun or on millions of suns at once. The result so far has been nothing. No such glow has been confirmed anywhere. A truly ancient, expansive civilization should have been hard to hide, because it would have left its heat smeared across the sky, and we do not see it. There's also a second limit on our searching that is easy to miss. And it is not about coverage at all. It is about time. Even if we built the perfect instrument tomorrow and swept the entire sky at every frequency at once, we would still only be sampling a single instant, the thin sliver of now in which we happen to be looking. A civilization that rose, flourished for a few thousand years, and fell quiet 1,000,000 years ago would have finished its entire broadcast long before our telescopes existed. Its signals would have washed past this region of space and faded into the background ages before the first human looked up. So the silence we hear is not only a silence of place, but a silence of timing. And that cuts both ways. It means our failure to hear anyone could simply be the misfortune of listening in the wrong century. But it also means something darker, because if civilizations are common and yet each one stays loud for only a brief flicker before going dark, then a galaxy that was once full of voices would still, right now, register as almost completely silent to us. A sky that was never inhabited, and a sky whose tenants have all fallen quiet can read, to a latecomer, as the same empty page. So set the whole search beside the whole silence. We have not found a single confirmed signal of intelligent origin. We have not found a single confirmed structure that betrays engineering on a vast scale. We have not found ancient probes parked in our own system, nor unmistakable ruins on any world we have visited, nor the waste heat of a civilization harnessing the power of an entire star. Across every wavelength we have managed to check, in every direction we have managed to point, the result keeps coming back the same. Nothing rises clearly above the natural background, and that is the precise point where this story stops being a comfortable astronomy lesson and becomes something with teeth. Because there are two fundamentally different ways to interpret a silent galaxy, and they could not be more opposed. The first interpretation is the gentle one. The galaxy is silent because it is genuinely empty, or nearly so. Life is far rarer than the abundance of planets would suggest. Intelligence rarer still, and we are simply alone or close to it. In that reading, the silence is just the natural quiet of a mostly lifeless cosmos, and there is nothing menacing about it. But there is a second interpretation, and it is the one that should make the hair on your arms stand up. What if the silence is not the quiet of an empty room, but the quiet that follows after something has happened? What if all those billions of habitable worlds did, in fact, give rise to life again and again across the long history of the galaxy? And what we are hearing is not the silence of a place where no one ever arrived, but the silence of a place where they arrived and then, for some reason, did not last. In that reading, the emptiness is not a sign that the road was never traveled. It is a sign that almost no one survives the journey. Those two readings demand completely different feelings about our own future, and we currently have no way to tell which one is correct just by listening. The same flat, featureless silence is consistent with both a galaxy that was always nearly empty and a galaxy that fills with life and then, again and again, goes dark. The data alone does not distinguish them. And if even a fraction of those billions of worlds did produce life, then the second reading is not paranoia. It is a serious possibility that demands a serious mechanism, some barrier severe enough, common enough, and unforgiving enough to silence nearly everyone who ever started up the same staircase we are climbing right now. There is a name for that barrier. There is a framework that takes the silence and treats it not as emptiness, but as evidence of failure, a hidden threshold somewhere on the long path from lifeless chemistry to a lasting, visible, star-spanning civilization. It is an idea precise enough to be argued over by serious scientists, and frightening enough that some of them openly hope it points in a particular direction. And the most disturbing thing about it is not the barrier itself. It is that the framework cannot, on its own, tell us where the barrier sits, whether it is a door humanity has already passed through or one we are walking toward at this very moment. To understand why that single uncertainty is so terrifying, we have to look closely at the idea itself and at the brutal staircase it describes. If the silence of the galaxy really is the second kind of silence, the quiet that settles after something has happened rather than the quiet of a place where nothing ever began, then we are forced to go looking for the thing that happened. We need a mechanism. Not a story, not a mood, but an actual barrier, severe enough and common enough to silence almost everyone who ever started climbing toward the stars. That is tall order. Whatever this barrier is, it has to apply across an enormous diversity of worlds, across billions of years, to creatures we cannot even imagine. And it has to work nearly every single time, because the galaxy is not partly quiet. It is, as far as we can tell, almost completely quiet. In 1996, a thinker named Robin Hanson, an economist with a deep interest in the deep future, sat down and gave that barrier a name. He wrote an essay with a title that already carried a chill inside it. He called it The Great Filter, and the subtitle asked the only question that really matters. Are we almost past it? Hansen's reasoning was clean and uncomfortable. He looked at the path that leads from a dead, lifeless planet all the way up to a civilization that spreads across the stars and makes itself unmistakably visible, and he pointed out something that is easy to overlook. That path is not a single jump. It is a long sequence of separate, difficult transitions, each one of which has to succeed before the next can even begin. And here is the crucial move. Hansen argued that somewhere along that sequence, there must be at least one step so improbable, so rarely cleared, that it acts like a filter. Material pours into the bottom of the sequence in vast quantities, trillions of planets, oceans of chemistry, eons of time, and almost nothing makes it out the top. The great filter is whatever that brutal narrowing is. It is the reason the galaxy can be drowning in potential and still appear empty. The filter is the gap between how much should have happened and how little actually did. Notice how neatly this idea slots into the Drake equation we just walked through. Remember those final terms, the ones we could not measure, the fraction of worlds where life begins, where it turns intelligent, where it builds technology, and how long that technology lasts. The great filter is simply the claim that at least one of those unmeasured terms is fantastically, crushingly small. The equation tells us that somewhere a number must be tiny, because the answer we observe is so close to zero. The great filter asks the next question, the dangerous one. Which term is it, and have we already passed it, or not? Now, before we go any further, I need to be very careful about what the great filter is, and what it is not. Because this is the single most misunderstood idea in this entire subject, and getting it wrong destroys the whole story. The great filter is not a prophecy. It is not a specific doom that someone has identified and dated. It is not a claim that on a particular Tuesday, a particular catastrophe wipes out every civilization. People hear the phrase and immediately picture one dramatic apocalypse, a single cosmic guillotine waiting at a fixed point. That picture is wrong, and it makes the real idea seem far more cartoonish than it actually is. The great filter is a structural observation, not a predicted event. It says only this. Given how many starting points there are and how silent the result is, at least one of the steps on the road from dead matter to a lasting spacefaring civilization must be extraordinarily hard to pass. It does not tell us which step. It does not tell us why. It does not even tell us that there is only one. The barrier could be a single, near impossible transition that almost nothing in the universe ever clears. Or it could be the combined effect of several merely difficult steps, each one survivable on its own, but so unlikely in sequence that the chain almost never completes from beginning to end. The hypothesis is a frame, a way of organizing the silence, and its honesty is part of why serious scientists take it seriously. It does not pretend to know the answer. It only insists that the silence demands one. And there is a subtle but vital point buried in the phrase extraordinarily hard. One we have to make explicit because it determines what kind of barrier we are even looking for. A filter cannot just be a difficult step. The kind that most worlds fail, but a respectable fraction survive. That would not produce the silence we see. Suppose, for the sake of argument, that some step is failed by 99 out of every 100 worlds that reach it. That sounds brutal, But begin with billions of worlds at the bottom, and even after that savage cull, you would still have tens of millions of survivors streaming through, more than enough to fill the galaxy with voices many times over. A barrier that merely thins the crowd does not explain a sky with no one in it. For the great filter to do its job, it has to be something close to absolute. A step failed not by 99 in 100, but by something like all but 1 in a billion, or 1 in a trillion. The silence is so complete that the filter cannot be a steep hill. It has to be very nearly a wall. That requirement is part of what makes the whole idea so unsettling, because a barrier that severe is not a common kind of obstacle. It is the kind of thing that almost nothing in the universe has ever gotten past. And we have to find a place on the staircase capable of being that merciless. To really feel the shape of the problem, we have to lay out the staircase itself, step by step, because the great filter has to be hidden on one of these stairs, and looking at them in order tells you just how many chances there are for the climb to fail. Picture it as a staircase rising out of a dark, lifeless ocean of chemistry, each step a transition that took our own world a vast stretch of time to achieve. The very first step is simply having the right kind of place to stand. You need a stable planet in a stable orbit, around a stable star, in a region of the galaxy calm enough to leave it alone for billions of years. The star cannot flare too violently. The orbit cannot wander into freezing dark or scorching heat. The world needs the right raw materials and enough time undisturbed for chemistry to get complicated. That sounds like a low bar given how many planets exist, and maybe it is, but it is not automatic. Plenty of worlds are sterilized by their stars, or frozen solid, or cooked, or never settle into the long stability that everything else depends on. The second step is the one that may be the most mysterious of all. Somehow, on the early Earth, dead chemistry became alive. Lifeless molecules sitting in water and energy arranged themselves into something that could copy itself, could carry information forward, could evolve. We call that transition abiogenesis, the origin of life from non-life. And the brutally honest truth is that we still do not understand how it happened. We can recreate fragments of the chemistry in laboratories. We can make some of the building blocks form under early Earth conditions. But the full leap from a soup of ingredients to a self-replicating, evolving system remains unexplained. We have exactly one confirmed example of life ever beginning, our own, and you cannot calculate the odds of an event from a single occurrence. Abiogenesis might be nearly inevitable wherever the conditions are right, igniting on countless worlds, or it might be a fluke so rare that it happens only once in a galaxy, leaving billions of warm, wet, perfectly suitable planets sitting sterile forever. We genuinely do not know, and that not knowing is itself a candidate for the filter. The third step is the first cell. Even once you have some self-copying chemistry, you need to wrap it up, organize it, give it a membrane and a metabolism, and produce the simplest true living cell, the kind we call a prokaryote, the lineage that includes bacteria. On Earth, this happened early and then dominated for an immense span of time. For roughly 2 billion years, life on this planet was nothing more than these simple, single cells. 2 billion years of life that never became anything more complicated than a smear of microbes. That long pause is worth noticing, because it hints that the next step up was anything but easy. The fourth step is the one that may be the strangest and most underappreciated leap in the entire history of life. It is the jump from a simple cell to a complex one, from a prokaryote to a eukaryote, the kind of cell that builds every plant, animal, fungus, and complex organism you have ever seen. The difference is enormous. A eukaryotic cell has a nucleus, internal compartments, and crucially, tiny power plants inside it that supply the energy for genuine complexity. And the way that happened appears to be a near miracle of circumstance. As best we can reconstruct it, one simple cell engulfed another, and instead of digesting it, kept it alive inside itself as a permanent partner. That swallowed cell became the energy factory that powers all complex life. This event, the merger we call endosymbiosis, may have happened only a single time in the entire history of life on this planet. Once. If a step that fundamental occurred just once on a world that was otherwise teeming with simple life for billions of years, then it is a powerful candidate for a filter that leaves countless planets stuck forever at the level of microbes, alive but never advancing. Now pause on that word once, because it turns out to be one of the most powerful tools we have for reading the entire staircase. A way of judging which steps are easy and which are deadly without ever leaving Earth. Here is the principle. Look at how many separate, independent times a given transition happened in the history of life on this single planet. If something evolved over and over in unrelated lineages by different roots, that is strong evidence the step is relatively easy, because life found it again and again once the conditions allowed. But if something happened exactly once in 4 billion years, on a world absolutely saturated with living things constantly experimenting, that single occurrence is a red flag. It whispers that the step is genuinely hard, that even with endless attempts and endless time, life cracked it only a single time. The number of independent origins is, in effect, a difficulty meter for each stair, and we can read it straight off the fossil and genetic record. The complex cell scores the worst possible mark on that meter. It registers exactly 1. Eyes, by contrast, evolved many separate times. Powered flight evolved several times. Even the trick of generating body heat appeared more than once. Each of those repeated inventions tells us that stair is climbable. The lonely, solitary origin of the complex cell tells us something very different and far more ominous. The 5th step is putting those complex cells together into bodies. Multicellularity, true cooperative organisms made of many cells working as one, with specialized parts and coordinated structure. And here, the difficulty meter we just built pays off immediately, because it reads in exactly the opposite direction from the complex cell. Multicellularity did not happen just once. It evolved independently many separate times across the history of life, in different lineages, by different roots. Plants did it, animals did it, fungi did it, various kinds of algae did it on their own. When a transition happens over and over in unrelated branches of the tree of life, that is the opposite of a filter. It is the sign of a step that is relatively easy once the pieces are in place. A step the universe seems to find again and again. So if we are hunting for the Great Barrier, this particular stair, the assembly of complex cells into bodies, is probably not where it hides. That matters enormously, because every stair we can confidently rule out as easy forces the filter to relocate, to crowd into the remaining steps. Reading the staircase is a process of elimination, and each repeated invention is a stair we can cross off the list of suspects. The 6th step builds on that. The rise of genuinely complex animals, with nervous systems, with senses, with the machinery that makes behavior and learning possible. The seventh step is intelligence. And here we have to be careful about what we mean, because not all intelligence is the same. Plenty of animals are clever. Many can solve problems, use simple tools, communicate, even pass knowledge to their young. But the staircase requires a particular and rare kind of mind, one that can build cumulative culture, abstract reasoning, language rich enough to carry ideas across generations, and let each generation start where the last left off. That specific capacity, as far as we know, has emerged to a technological degree exactly once on this planet, in us, despite the Earth being filled with intelligent animals for tens of millions of years. Run that through our difficulty meter, and the reading is uncomfortable. A single origin on a world full of clever creatures earns the same damning mark as the complex cell, which is exactly why some thinkers place a candidate filter right here, at the leap to technological intelligence itself. The eighth step is technology itself. The moment a species stops merely living in its environment and starts reshaping it, building tools, harnessing energy, and eventually sending signals out into the void, becoming for the first time detectable across space. And there is a ninth step, the one we are most interested in, and the one we have never witnessed anywhere, ourselves included. That is the step from a young, fragile, newly technological species into a durable, long-lived, far-spreading civilization, one that survives long enough and expands far enough to become unmistakably visible across the galaxy and to stay visible for ages. That is the top of the staircase. That is the kind of civilization whose absence creates the entire paradox. And we have not yet taken that step. We are standing on the eighth stair, having just learned to broadcast, looking up at a ninth step we have not climbed, with no idea how many others reached this exact landing and went no further. Now look at that staircase as a whole, and the logic of the great filter snaps into focus. Each step is a transition that can fail. Each one is a place where the climb can simply stop, where a world can stall out and remain there for the rest of its existence. The hypothesis says that at least one of these steps is a true filter, a stair so tall, or so slick, or so rarely cleared that almost everything attempting the climb falls there and never rises again. Maybe it is a single, impossible stair. Maybe it is the accumulated difficulty of several merely hard ones, each shaving the survivors down further until the number that reach the top approaches 0. Either way, the filter is somewhere on those stairs. The silence guarantees it. Think of it less like a staircase for a moment and more like a combination lock with many tumblers. For the lock to open, every tumbler has to fall into exactly the right position, in the right order. Get one wrong and nothing opens, no matter how perfect the rest are. Each step on our staircase is a tumbler. A world can get the planet right, get the chemistry right, get the first cell right, and then fail at the merger that makes complex cells, and the lock stays shut forever. Trillions of worlds rattling at the lock, and almost none of them clicking all the way open. That is the picture the Great Filter paints, and it is consistent with everything we observe, including the crushing quiet. But here is where Hansen's idea turns from a clever piece of bookkeeping into something that reaches directly for your future. Because the question is not only whether the filter exists, the question is where on the staircase it sits relative to us, and that single detail changes everything. There are only two broad possibilities, and they are mutually exclusive, and they could not feel more different. The first possibility is that the filter is behind us. It lies on one of the lower stairs, a step we have already, somehow, climbed. Maybe the origin of life is the near impossible step, and the reason the galaxy is silent is that dead chemistry almost never wakes up, leaving most of those billions of habitable worlds sterile for all time. Maybe the filter is that single freakish merger that created complex cells, a step so rare that most living worlds stay stuck as microbial films forever. If the filter is one of these early stairs, then the silence is not a warning about our future at all. It is a record of our improbable luck. It means we are the rare climbers who made it past the impossible step, and the road ahead, while difficult, is open. In that version of the story, the empty galaxy is strangely good news. We survived the thing that stops nearly everyone, and the quiet sky is the echo of all the worlds that did not. The second possibility is the one that should make your stomach tighten, because it is the exact mirror image. What if the filter is not behind us? What if all those early steps, the ones that feel so improbable when we look back at them, are actually fairly common across the galaxy? What if life ignites readily? Complex cells arise more than once. Intelligence and technology emerge again and again on world after world, and the staircase is climbed, up to roughly the stair we are standing on, by countless species. If that is the case, then the filter cannot be behind us, because it would have stopped all of them long before they reached this point, and clearly it did not. Which means the filter has to be somewhere on the stairs we have not yet climbed. It lies ahead. It is the step from a young technological species into a lasting, visible, spacefaring one, and the silence is telling us that almost no one survives that step. In that version, the empty galaxy is not a record of our luck. It is a preview of our fate. This is the heart of what makes the Great Filter so much more disturbing than a simple sad fact about cosmic loneliness. It contains a hidden, almost cruel logic, and Hansen stated it plainly. There is an inverse relationship between how easy it is for life to reach our stage and how good our own odds are. The more ordinary we turn out to be, the more dangerous our position becomes. If we discover that the early steps are easy, that life and even intelligence are common, we do not get to feel less alone in a comforting way. Instead, we have to confront the fact that all those others reached roughly where we are and then vanished, which means the thing that erased them is still in front of us, still waiting, still unbeaten. Turn that logic over, and it produces one of the most counterintuitive conclusions in all of science. Every piece of evidence that life is common is, from the Great Filter's perspective, potentially bad news. Find simple microbial life on another world, life that arose independently of Earth, and you have just shown that abiogenesis is not the rare filtering step, which pushes the filter higher up the staircase, closer to us. Find complex life, independently evolved, and you push the filter higher still. The further up the stairs we find that others have climbed, the less room remains below us for the filter to hide, and the more it is forced into the space above us, into our future. The optimist's dream, discovering that the universe is full of life, would for a great filter theorist be a quiet kind of nightmare, because each discovery would shrink the comforting possibility that the hardest part is already done. And this is why the silence alone, by itself, can never tell us where the filter sits. The silence is perfectly consistent with both readings. A galaxy where the filter is an early step, where life almost never begins, would look silent, because there would be almost no one to hear. but a galaxy where the filter is a late step, where life and intelligence are common but nearly always destroy themselves or fail before spreading, would look exactly identically silent, because everyone who started up the stairs fell before they could become visible. Two completely opposite situations, one reassuring and one terrifying, producing the same flat, featureless quiet. You cannot tell them apart just by listening. The sound of a galaxy where we are the rare survivors, and the sound of a galaxy where we are the next to fall, are the same sound. They are both silence. That is the trap built into the heart of this hypothesis. The one thing we can most easily observe, the absence of signals, is the one thing that refuses to answer the only question that matters. It confirms that a filter exists. It says nothing about whether that filter is a closed door behind us or an open drop ahead of us. We are left holding a fact with two meanings, one a story of survival and one a story of doom, and no way from the silence alone to know which story we are living inside. So if the silence cannot locate the filter for us, what can? The only way to even begin pinning it down is to stop staring at the empty sky and start reading the evidence of the climb itself. We have to look hard at the lower stairs we have already passed and ask how difficult each one truly was. We have to study the origin of life, the rise of complex cells, the emergence of intelligence, and try to judge whether any of those steps was rare enough on its own to be the Great Barrier. And we have to look outward at the worlds around us, searching for any independent example of life at any level, because every such example would shift the filter's likely position. The location of the door is not written in the silence, it is written in biology, in geology, in the deep history of our own planet, and in whatever we manage to find on the planets and moons of other stars. There is a hopeful version of that investigation, a case to be made that the hardest stair is already far below us, that we are the improbable survivors of a barrier almost no one clears, and that the road upward, however steep, is genuinely open. It is a case built on the strangeness of life's origin, and on that singular once in 4 billion years merger that built the complex cell. But that hopeful case has recently been challenged from an unexpected direction, by scientists arguing that we may not be the lucky freaks we'd like to imagine, and the argument, if it holds, quietly pushes the door in exactly the direction we least want it to go. To see why the comforting story might be a trap, we have to climb back down the staircase and examine, one stair at a time, the steps we've already survived. Let us begin with the version of the story that lets you sleep at night. If the great filter is real, and the silence insists that it is, then the kindest place for it to be hiding is far below us. On a stair we have already climbed, a barrier we cleared so long ago that we have forgotten it was ever there. In that reading, we are not a species walking toward a cliff. We are a species that already walked along the edge of one, blindfolded, and somehow did not fall. The empty galaxy becomes a monument to our luck rather than a forecast of our death. So before we turn to the darker possibilities, we owe this hopeful case a fair and serious hearing, because the evidence for it is genuinely strong, and the people who believe it are not fools. The argument that the filter lies behind us rests on a simple, almost intuitive observation. When you look back down the staircase from where we stand, certain steps look absurdly improbable. They look like the kind of thing that should almost never happen. And the fact that they happened here, on this one world, starts to feel like winning a cosmic lottery. If even one of those early steps is as rare as it appears, then it alone could be the filter. And we would already be on the far side of it. The first and most obvious candidate is the one we have circled twice already: the origin of life itself. Think honestly about what abiogenesis requires. You need a planet to take a churning, lifeless mixture of simple molecules and somehow, through no guiding hand, assemble them into a system that copies itself, stores information, and improves across generations. We have searched for the recipe for decades. We can produce some of the ingredients. We can coax fragments of the chemistry into existence in a laboratory. But the full leap, the moment dead matter first became something that could be said to be alive, remains genuinely unexplained. And here is the statistical trap that makes it such a tempting filter. We have exactly one confirmed case of life beginning in the entire universe, and it is our own. From a single data point, you simply cannot calculate a probability. Abiogenesis might happen readily on any warm, wet world, or it might be a fluke so staggeringly rare that it has occurred only once across the whole galaxy. If it is that rare, then the filter is right there at the bottom of the staircase, and the billions of habitable but sterile worlds out there are exactly what you would expect to find. We would be the one place where the impossible spark caught. There is, however, a piece of evidence on Earth itself that quietly argues against this comforting idea, and is worth sitting with. Life on our planet appears to have begun astonishingly early. Almost as soon as the young Earth had cooled enough to hold liquid water and stopped being bombarded into sterility, life was already here. The traces of it reach back nearly as far as the rocks themselves. Now, if abiogenesis were a fantastically improbable accident, the kind of event that needs billions of years of lucky rolls to occur, you would not expect it to happen the moment the planet became habitable. You would expect a long, long wait. The fact that life appeared so promptly, almost eagerly, hints that beginning may not be the hard part at all, that given the right warm, wet chemistry, life starts readily. And if that hint is correct, then the origin of life is not our filter, which means the barrier must lie somewhere higher up, closer to us. Notice how that one observation, the early arrival of life, quietly works against our comfort. The second candidate sits a little higher up, and to many biologists, it is the more persuasive of the two. It is the strange, singular event that built the complex cell. Recall the shape of it. For something like 2 billion years, an almost unimaginable stretch of time, life on Earth went no further than simple cells, the bacteria and their kind. 2 billion years of the planet being alive, and yet never producing anything more elaborate than microscopic films and mats. Then, apparently just once, one simple cell engulfed another, and, rather than consuming it, kept it alive inside itself as a permanent partner, an internal power plant. That merger, the event called endosymbiosis, is the foundation of every complex cell in every plant, animal, and fungus that has ever existed. And the crucial detail is that, as far as we can reconstruct the deep history of life, it seems to have happened only one time, not repeatedly, not on many parallel lineages, once. A step that fundamental occurring a single time, on a world soaked in simple life for 2 billion years, is precisely the signature you would expect from a true filter. It would leave the galaxy full of living worlds that never advance beyond a microbial smear, alive but forever silent, forever stalled on the fourth stair. And there is a deep reason, rooted in raw energy, why this particular step may be so brutally hard. A reason that has nothing to do with luck and everything to do with physics. Some biologists argue that simple cells are trapped by an energy ceiling they cannot climb past. A bacterium generates power across its outer membrane, which means the bigger and more complex it tries to become, the worse its energy supply gets relative to the number of genes it must run. There is, in effect, a tax on complexity that simple cells simply cannot afford. They are stuck, not because evolution never tried to make them more elaborate, but because the books never balance. What that one ancient merger did was extraordinary. By taking another cell inside itself and turning it into a dedicated power plant, the host suddenly had internal energy generators, many of them, each with its own small set of genes devoted to nothing but producing power. Those internal power plants, the things we call mitochondria, gave the complex cell an energy budget per gene thousands of times larger than any bacterium could ever reach. For the first time, a cell could afford to carry a vast library of genes, to grow large, to specialize, to become intricate. In this view, the leap to the complex cell was not just unlikely, it required breaking through an energetic wall that, on most living worlds, may never be breached at all. The galaxy could be full of planets coated in bacteria that are stuck against that wall forever, alive and going nowhere. There is a related candidate hiding inside that same long pause, one that points not at the cell, but at the air. Complex, energy-hungry life needs oxygen, and the early Earth had almost none. For most of its history, the planet's atmosphere was effectively unbreathable to anything like us. Then, slowly, microbes that had learned to photosynthesize began releasing oxygen as a waste product. And over an immense span of time, the atmosphere transformed. We call that turning point the Great Oxidation Event. But even after it, the world did not rush toward complexity. There followed a vast sluggish stretch of time that geologists have nicknamed, only half in jest, the Boring Billion, a period of roughly 1 billion years in which the planet's chemistry seems to have idled in a stable, low oxygen state, and complex life simply did not take off. Whether the holdup was the slow accumulation of oxygen or some other planetary bottleneck, that enormous delay is itself a candidate filter. It suggests that even a living world, even one that has built complex cells, can sit stalled for 1 billion years or more, waiting on a planetary condition that may never arrive at all on most worlds. And there is one more early stare worth naming, because it is so easy to overlook and yet so consequential. It's the invention of a particular way of reproducing, the shuffling and recombining of genes that biologists call meiosis, the machinery behind sex. It sounds almost trivial beside the drama of the first cell or the first breath of oxygen, but consider what it does. When organisms simply copy themselves, every offspring is a near clone of its parent, and useful new traits arise only through the slow drip of random mutation. But when two parents combine and reshuffle their genes, evolution gains an enormous new engine, mixing variations together, recombining them in fresh ways, testing combinations far faster than mutation alone ever could. Without that engine, it is not obvious that complex, rapidly adapting, large-bodied life could ever have gotten going at all. And like the others, this innovation may have been a singular, difficult event in the deep history of complex cells. Every one of these candidates, the energy wall, the breathable air, the shuffling of genes, is a place where a living world might stall for the rest of its existence. Notice, too, that these early stairs may not be wholly separate obstacles standing in a row. and that subtlety matters for how we read them. They may be linked, each one quietly setting up the next, so that clearing one does not just pass a single test, but unlocks the door to the one after it. The microbes that learn to photosynthesize are the very ones that fill the air with oxygen, and that oxygen is the fuel the complex cell needs to run its energy-hungry way of life, which in turn makes large, active, multicellular bodies possible. Pull one of those threads and the others move. This is why the line between the behind-us candidates can blur. The filter may not be a single isolated stair at all, but a chain of coupled transitions that have to fall into place in the right order, each waiting on the last, which is exactly the kind of tightly linked sequence that almost nothing completes. Stack these candidates together and the comforting case writes itself. Perhaps the road from a dead planet to simple life is hard. Perhaps the road from simple cells to complex ones is harder still. Walled off by an energy barrier almost nothing breaks through. Perhaps the long wait for a breathable world is a bottleneck most planets never clear. If any of those is the Great Barrier, then we have already passed it. We are the improbable survivors, and the silence around us is the sound of all the worlds that got stuck where we did not. In this picture, the future is not a wall, it is open road. We climb the impossible stair without knowing it, and everything above us, however difficult, is at least achievable. That is the hope, and it is a real and respectable position. But hope in science is not the same thing as evidence. And this is exactly the point where a recent and serious challenge enters the story. One that threatens to pull the comforting reading apart. To understand it, you have to know where the whole idea that we are improbable came from in the first place. Because it did not start with Hansen. It started decades earlier with a physicist named Brandon Carter. In 1983, Carter made an argument that has shaped this entire field ever since, and it was deceptively simple. He looked at two numbers and noticed they were suspiciously close. The first number is how long it took intelligent life to evolve on Earth, from the formation of the planet to the appearance of us, which is something like 4 billion years. The second number is the total length of time the Earth will remain habitable before the aging sun eventually makes the surface uninhabitable, which is also measured in billions of years and is not enormously larger than the first. Carter argued that if evolving intelligence were easy, it should have happened quickly, leaving a vast, comfortable margin of habitable time to spare. Instead, it took nearly the entire available window. To him, that near coincidence was a clue. It suggested that getting to intelligence required passing through a series of steps that were each intrinsically improbable, so improbable that the whole sequence barely squeaked through before the clock ran out. This became known as the hard steps model, and its conclusion was bleak for anyone hoping for company. If our own existence required clearing several intrinsically unlikely hurdles, then technological life like ours should be, in Carter's words, exceedingly rare across the universe. For roughly 40 years, that argument stood as a pillar supporting the comforting reading of the Great Filter. The hard steps model said the early stairs were brutally improbable, which placed the filter behind us, which meant we were rare survivors. It fit the silence. It fit the intuition. It felt right. Then, in early 2025, a team of researchers published a direct and carefully argued challenge to it, and it landed hard precisely because it did not come from wishful thinkers. It came from geobiologists and astronomers working together. Daniel Mills, Jennifer McCalady, Adam Frank and Jason Wright, publishing in a major peer-reviewed journal. They re-examined Carter's core assumption through the lens of Earth's actual geological history, and they proposed something genuinely subversive. What if there were no hard steps at all? What if the long delay before intelligence appeared was not evidence of improbability, but evidence of something completely different? Something about the planet itself? Their reasoning runs like this. Carter assumed that the timing of each evolutionary step was governed by intrinsic improbability, by how unlikely the step was in itself. But the Earth was not a fixed, ready stage waiting for life to perform on it. The Earth changed dramatically over its history, and many of its early conditions were actively hostile, not just to complex life, but to the very steps that complex life requires. Consider oxygen again. Complex animal life needs a substantial amount of free oxygen in the atmosphere to power its high-energy way of living. But the early Earth had almost none, and it took billions of years of patient microbial work to build the breathable air we now take for granted. So the question is not, why did complex animals take so long to evolve because the step was so improbable? The question becomes, when did the planet finally become a place where complex animals were even chemically possible? In this view, the great delays in Earth's history were not waiting periods for improbable accidents. They were waiting periods for the planet to prepare the stage. Each major evolutionary leap, the team argues, became possible only when the global environment crossed into a new permissive state, when a fresh window of habitability opened. The origin of complex cells, the rise of multicellular animals, the eventual emergence of intelligence, each one appeared not after some impossible lottery was finally won, but relatively soon after the world became capable of supporting it. Life, in this picture, did not arrive early or late. It arrived on time, tracking the slow transformation of the planet beneath it. You can see this idea written into one of the most dramatic moments in the whole fossil record, the event geologists call the Cambrian explosion. For billions of years, life stayed small, soft, and simple. Then, in a relatively short stretch of geological time, complex animals seemed to burst onto the scene almost all at once. A sudden riot of bodies, shells, eyes, limbs, and predators, the ancestors of nearly every major group of animals alive today. For a long time, that abruptness looked like a mystery, even a miracle. But through the lens of the new model, it looks like something else, like a door finally opening. Once oxygen had climbed high enough, once the chemistry of the oceans and air had crossed the right thresholds, complex animal life did not need a miracle to appear. It rushed in to fill a stage that had only just become habitable for it. The explosion was not life beating impossible odds. It was life arriving promptly the moment the planet was ready. Sit with what that reframing does, because it is not a small adjustment. If Mills and his colleagues are right, then the long 4 billion year march to intelligence is not proof that intelligence is a fluke. It is just proof that planets take a long time to become hospitable to it. And if that is true, then the steps on the staircase that we thought were nearly impossible might not be improbable at all. They might be the natural, even expected outcome of a planet and its life evolving together. Given enough time, the eukaryotic cell, the multicellular body, the thinking brain, all of them might be probable results of biology and geology working in tandem on any world that stays stable long enough. Humans, and human-like life beyond Earth, might represent not a cosmic accident, but a likely product of planetary maturity. Now you might think that this is good news, that it makes the universe friendlier and our existence less lonely. And in one sense, it does. But here is where you have to remember the cruel inner logic of the Great Filter that we built so carefully earlier, because this is exactly where that logic comes back to bite. If the early steps are not the filter, if life and complexity and even intelligence are reasonably probable outcomes given a stable planet and enough time, then the comforting reading collapses. The filter cannot be behind us, because if those early stairs were easy to climb, then countless other species across the galaxy climbed them too, reaching roughly where we are. And they are not here. The galaxy is still silent, which means the barrier that stopped them did not stop them on the lower stairs. It stopped them somewhere above the stair we are standing on. It stopped them in their future, which is to say, potentially in ours. This is the double edge that makes the hard steps debate so much more than an academic squabble about evolutionary timing. The traditional Carter view that the early steps are improbable was frightening in one way, suggesting we might be nearly alone. But it was also strangely comforting, because it placed the filter behind us. The new challenge to it removes that comfort. By arguing that intelligence is not a fluke, it quietly slides the filter forward, from our deep past toward our unknown future. The more ordinary and reproducible our origin turns out to be, the more we are forced to confront the possibility that the deadliest barrier is not one we have already survived, but one we have not yet reached. And notice, crucially, that this is a genuine, live scientific debate, not a settled answer. The hard steps model has not been overturned. It has been seriously challenged. Reasonable experts now disagree about whether our existence was a near miracle or a near certainty, and that disagreement is precisely the disagreement about whether the filter is behind us or ahead of us. We do not know which camp is right. We only know that the stakes of the question are our entire future. If the location of the filter depends so heavily on how easy the early steps really are, then there is one kind of evidence that could begin to settle it. Evidence we have been straining to find for years. We need to know whether life ever began anywhere other than Earth. Because remember the rule we established. Every independent example of life we find, at any level of complexity, pushes the filter higher up the staircase, closer to us. Find life that arose on its own somewhere else, and you have proven that abiogenesis is not the rare filtering step. You have shown that the spark catches in more than one place, which means the bottom of the staircase is not the barrier, which forces the filter upward toward our stage and beyond. This is why the search for life on other worlds is not just a romantic quest for cosmic company. It is, from the perspective of the Great Filter, a search for the location of the door, and it carries a strange dread inside it. Because in this framework, finding life is not unambiguously good news. It might be the most ominous discovery we could possibly make. The remarkable thing is that we no longer have to look only at distant stars to test this. Our own solar system holds several places where a second, independent origin of life might be hiding, and we are actively going to check. Mars is the first. We now know it was once a warmer, wetter world, with rivers, lakes, and possibly seas, exactly the kind of place where life might have started in its youth before the planet dried and froze. Robots are crawling its surface right now, drilling into ancient mud, searching for any chemical whisper that something once lived there. Then, there are the ocean moons, and they may be the most exciting targets of all. Beneath the cracked icy shell of Jupiter's moon, Europa lies a vast, dark, liquid ocean, holding more water than all of Earth's oceans combined. Around Saturn, the small moon Enceladus does something astonishing. It sprays jets of water from a hidden ocean straight out into space through cracks at its south pole. And our spacecraft have flown through those plumes and tasted them, finding salts and organic molecules the raw chemistry life would need. And further out, Saturn's moon titan runs a wholly alien chemistry, with rivers and lakes not of water but of liquid methane, a place so strange it forces us to ask whether life could take a form we have never imagined. Each of these worlds is a separate test of the same crucial question. If we drill into Mars and find the fossil of a microbe that arose on its own, or fly through the spray of Enceladus and catch a signature of something alive, we will have shown that life began at least twice in this one small solar system. And if it happened twice here, by ordinary chance, then it must be happening constantly across the galaxy, on countless worlds. That discovery would be celebrated everywhere as the greatest in history. But for anyone who understands the Great Filter, it would carry a quiet chill, because a second Genesis next door would slam shut the comforting possibility that the origin of life is our protective barrier. It would push the filter up the stairs, toward us, toward the steps we have not yet climbed. That is exactly why the contested discoveries of recent years have been watched with such intensity. There was the claim of a strange gas called phosphine high in the clouds of Venus, a molecule some argued should not be there without life to make it. A claim that has been fiercely debated and remains unresolved. And there was the far more dramatic candidate that captured headlines around the world, a distant planet called K218b, a world considerably larger than Earth, orbiting a small red star far enough away that its light takes more than a century to reach us. It is what astronomers call a sub-Neptune, and some researchers proposed it might be a particular kind of world with a deep global ocean beneath a thick, hydrogen-rich atmosphere, a setting where life, in principle, could exist. In 2023, a team using the James Webb Space Telescope studied the light filtering through that planet's atmosphere and reported detecting certain molecules, including a tentative, weak hint of one called dimethyl sulfide. That molecule matters enormously, because on Earth, dimethyl sulfide is produced almost entirely by life, much of it by marine organisms in the oceans. To even whisper its name in the context of another planet's atmosphere is to raise the possibility of a biosignature, a chemical fingerprint of biology. Then, in the spring of 2025, the same team announced new observations using a different instrument on the same telescope, and reported features they interpreted as consistent with dimethyl sulfide, and possibly a related molecule, dimethyl disulfide. At a confidence level, they described as around 3 sigma. For a brief moment, headlines around the world treated it as though we might have found the first chemical sign of life beyond Earth. But this is exactly where scientific discipline matters, and where the gap between a candidate and a confirmation becomes everything. 3 sigma sounds impressive to a casual listener, but in this field it is nowhere near the standard required to claim a discovery. The gold standard is 5 sigma, a level of confidence that makes a chance fluke extraordinarily unlikely. A 3 sigma signal is a hint, an invitation to look harder, not a verdict. And when other teams looked harder, the signal did not hold up. Through the rest of 2025, multiple independent groups reanalyzed the very same telescope data using their own methods and their own assumptions. One after another, they reached sobering conclusions. Some confirmed that the planet's atmosphere contained methane, a real and solid result, but found no statistically significant evidence for the biosignature molecules at all. Others showed that the apparent features sat so close to the level of instrumental noise that they could not be reliably distinguished from it, and that several other completely non-biological molecules fit the same data just as well. A comprehensive joint analysis combining observations across the full range of wavelengths concluded that there was insufficient evidence for dimethyl sulfide or dimethyl disulfide, and that ordinary chemistry could account for what was seen. By the latter part of the year, the broad consensus of the community had moved decisively away from the original claim. The candidate had not been confirmed. It had, for the most part, been set aside. It is vital to be precise about what this episode does and does not mean, because it is easy to draw the wrong lesson. It does not mean K218b is definitely lifeless. It does not mean the search has failed. What it demonstrates is the rigor that separates real conclusions from premature ones. A genuine detection of life beyond Earth would have to survive exactly this kind of relentless, independent scrutiny, and the K218b claim, fascinating as it was, did not. So as things stand, we have no confirmed evidence of life anywhere but Earth, not a single microbe, not a single unambiguous biosignature. The bottom of the staircase remains, for now, a mystery with a sample size of 1. And that lack of confirmation leaves us suspended in precisely the uncertainty that makes the Great Filter so maddening. We cannot yet locate the door. The hopeful case that the filter is the rare origin of life or the singular birth of the complex cell remains possible, which would mean we are improbable survivors with open road ahead. But the recent challenge to the hard steps model has weakened that hope by arguing that our origin may not have been improbable at all, which would slide the filter forward into our future. And the one tool that could begin to decide between them, the discovery of independent life elsewhere, has so far given us nothing solid to work with, only contested gases and candidates that dissolved under examination. Every avenue we have explored to find the filter behind us has come back inconclusive at best, and quietly discouraging at worst. So we are forced to turn and look the other way, up the staircase, into the steps we have not yet climbed. If the filter is not safely behind us, if the growing suspicion is that life and intelligence are more common than we once believed, then we have to take seriously the possibility that the Great Barrier lies ahead, on the stair between a young technological species like ourselves and a lasting, visible, spacefaring civilization. We have to ask, what could possibly be so deadly about that particular step that it silences nearly everyone who reaches it? And the most unsettling part of that question is that, unlike the ancient steps far below us, this one is not hidden in some other planet's deep past. If it is real, it is the step we are standing in front of right now. So we turn around. For a long while now, we have been looking backward and downward, studying the long climb behind us, asking whether the Great Barrier was some ancient stair we already cleared without knowing it. And every honest attempt to confirm that comforting answer has come back inconclusive. The origin of life remains a mystery with a sample size of 1. The challenge to the hard steps model has weakened our claim to be improbable survivors. The one candidate biosignature that might have begun to settle the question dissolved under scrutiny. The case for a filter safely behind us is not dead, But it is no longer something we can lean on with confidence, and so we are forced to do the thing we have been avoiding. We turn around and we look up into the steps we have not yet climbed. Here is the first thing that makes the upward view so much more frightening than the downward one. The ancient steps, the ones far below us, are abstract. They happen to microbes, to single cells, billions of years ago, on a planet that no longer exists in the form it did then. We can study them with the cool detachment of historians. But the step directly above us is not abstract, and it is not ancient. It is the step from a young, newly technological species into a lasting, visible, spacefaring civilization. And we are standing on the edge of it right now. If the filter lies ahead, it is not hidden in some other world's deep past. It is the threshold beneath our own feet. And unlike every stair below us, this one comes with a unique and terrible feature that the climber is powerful enough to destroy itself. Think about what actually changes at the stair we occupy. For the entire history of life on Earth, the dangers that could end a lineage came from outside it. A wandering asteroid, a shifting climate, a nearby star convulsing. The creature itself was never the threat. But intelligence and technology break that pattern completely, because the very same capabilities that let a species become detectable across space, the mastery of energy, the manipulation of matter, the building of tools that reshape a world, are also the capabilities that let a species end itself. This is the structural insight at the heart of every argument that the filter lies ahead. The visibility we are looking for and the danger we are afraid of grow from the same root. You cannot become loud enough to be heard across the galaxy without first becoming powerful enough to silence yourself. Power, in other words, arrives long before the wisdom to handle it, and the gap between the two is exactly where a late-stage filter would live. And there is a sharpening detail hidden in the Drake equation that makes this stair even more precarious. The very last term. The one we flagged earlier. The one that asks how long a civilization stays detectable. Look at our own case. We've been broadcasting in a way that could conceivably be noticed for only about 100 years. That is the entire span of our visibility so far. A single century against the galaxy's 13 billion years. If technological civilizations typically last only a few centuries in a detectable state before they fall quiet, whether through catastrophe or simply through going silent, then at any given moment, almost none of them would overlap with us closely enough to be heard. The galaxy could have hosted thousands of civilizations across its history, each one a brief flicker, each one already dark by the time its light could reach us, and the sky would still look exactly as empty as it does. A short, detectable lifetime alone can produce a silent galaxy, and we have no idea yet whether ours will be short or long. But before we let that thought soften the contradiction too much, we have to confront an idea that makes the late filter far harder to escape. Because it suggests that even a civilization that does not survive should have left something permanent behind. The idea builds on a concept from the mathematician von Neumann, who described machines that could copy themselves, and which later thinkers turned into something simple and devastating when pointed at the stars. Imagine a single probe, a robotic craft built to travel to a nearby star system, and once it arrives, to mine raw materials and build copies of itself, which then fly onward to new systems and repeat the process. You do not need to send many, you need to send one. Because each probe builds more, the number grows not by addition, but by doubling, and doubling, and doubling again. Run that exponential spread even at modest speeds, and the mathematics says a single civilization could blanket the entire galaxy with self-replicating machines in a few million years. A blink of cosmic time. The crucial point is that these machines would outlast their makers. A civilization could rise, build one such probe, and then fall silent forever, and its probes would keep going, keep building, keep spreading, long after the builders were gone. So the galaxy should be full of them, dormant or active, parked in system after system, including ours, and yet we see no trace of any such machine. That absence sharpens the knife. It is not enough to say civilizations die young, because their durable, self-replicating tools should still be here even if they are not. The silence has to swallow not just the civilizations, but everything they could ever have sent out ahead of them. Now I have to be extremely careful here, more careful than at any other point in this story, because this is the moment where the whole subject is most often abused. It would be very easy to slide into saying that every intelligent species inevitably destroys itself, that the universe simply kills every civilization, that we are definitely next. Those statements are not the great filter. They are cheap melodrama wearing its clothes. The hypothesis does not claim that doom is certain, and it does not identify a single proven cause. What it says is far more disciplined and, in a way, far more unsettling. It says that if the early steps are common, then something on the upper stairs stops nearly everyone, and we do not know what it is, whether it is one barrier or several, or whether we will be among the few who pass it. So as we walk through the candidates for a filter ahead, hold that discipline firmly. We are not predicting our death. We are surveying the possible shapes of a danger whose existence the silence implies, but whose nature it refuses to name. The most obvious candidate, the one that has haunted this conversation since the 1950s, is self-destruction through our own weapons. And here we have to separate what is confirmed from what is merely feared, because the two are very different. What is confirmed, beyond any doubt, is the capability. Within a few short years of learning to split the atom, humanity built an arsenal capable of devastating its own civilization. That is not a hypothesis. That is a fact of the 20th century. What is also part of the historical record is how close that capability has come to being used, not through grand decisions, but through misread signals, faulty sensors, and the judgment of individuals in moments of confusion. We have walked up to that edge more than once and stepped back. What is a hypothesis, and only a hypothesis, is the idea that this kind of self-destruction is the great filter, that nearly every species which discovers such power eventually fails the test it creates. The physics that makes such weapons possible is universal. Any technological species, anywhere, will eventually uncover it. If even a portion of them fail to survive the discovery, that alone could carve a deep notch into the galaxy's potential. But notice the honest limit of the argument. We have one example, and that example has so far survived. We cannot calculate the odds from a single ongoing case. We can only say that the danger is real and that the test is one we have not finished taking. A second candidate has grown more prominent as our own tools have advanced. And it is in some ways more disturbing than the first, because it does not require a superpower to wield. It is the danger of engineered hazards. The possibility that as a civilization's technology matures, the ability to cause catastrophe spreads into more and more hands. Consider biotechnology. The same understanding of life that lets a species cure its diseases and feed itself also, in principle, gives it the power to engineer organisms that could do tremendous harm. A recent line of scholarly work has explored exactly this idea, modeling how the lifetime of a technological civilization might be shaped not by a single doomsday weapon controlled by a few, but by the slow democratization of dangerous capability across an entire population. The unsettling logic is that a civilization does not need most of its members to be reckless. It only needs the destructive power to become accessible enough, and the number of opportunities for catastrophe large enough that over a long span of time the probability of disaster creeps towards certainty. This remains a hypothesis, a model, not a confirmed mechanism. But it captures something genuinely worrying about the trajectory of any species that grows more capable faster than it grows more careful. The third candidate is the newest and, to many, the most provocative, and it concerns the very kind of intelligence that may someday read or build something like the words I am speaking now. In 2023, the astronomer Michael Garrett published an argument that artificial intelligence itself might function as a great filter. His reasoning starts from a pattern. Any civilization that develops radio technology and begins reaching toward the stars will, before very long, also develop machines capable of matching and then exceeding the intelligence of their creators. And the window between those two milestones, he suggested, might be startlingly short, perhaps only a couple of centuries. If that transition tends to happen quickly, and if it tends to be difficult or impossible to control, then most civilizations might pass through it before they ever manage to spread beyond their home world, becoming silent not through a war they chose, but through a transformation they could not steer. I want to stress as clearly as I can that this is a speculative hypothesis, not a confirmed finding. It rests on assumptions about how such a transition unfolds that we simply cannot test, because we have never witnessed it anywhere, including here. But it belongs on the list because it is a serious attempt to identify why the upper stairs might be so deadly, and because the timescale it points to, a mere couple of centuries between becoming detectable and losing control, is uncomfortably close to the span we ourselves have occupied. The fourth candidate is quieter than the others, and precisely because it lacks drama, it may be the most insidious. It is not a bang at all. It's a slow exhaustion. The possibility that civilizations commonly fail not through a single catastrophe, but through the gradual loss of long-term stability. A species that grows rapidly, consuming the resources of its world faster than it can replace or replenish them, may bend its own curve of progress until it breaks, sliding back from the threshold of the stars before it ever crosses it. Some researchers have framed this as a kind of burnout, an almost thermodynamic tendency for any expanding civilization to eventually outrun the capacity of its planet to sustain it. In this version, the galaxy is not littered with the ash of sudden wars. It is dotted with the cold remains of societies that simply could not maintain themselves long enough, that reached a level of complexity they could not afford, and quietly contracted. The silence in this reading is the sound not of explosions but of exhaustion. And there is a fifth candidate proposed only very recently, in early 2026, which adds a strange new dimension to the conversation. A modeling study suggested that as a species advances and rises to the top of its world, the same forces of comfort and intelligence that mark its success might steer it toward having fewer and fewer offspring until its population peaks and then declines, potentially toward collapse over a long span of time. The authors gave this filter a name drawn from the study of populations, exodemography, and they speculated that such a dynamic of voluntary depopulation might apply not only to us but to advanced species generally, quietly thinning them out of existence without a single shot fired. I present this exactly as it is, a recent and frankly speculative proposal, one model among many, not an established result, but I include it because it illustrates something important about this whole field. New candidate filters are still being proposed. The space of ways a civilization might fail after reaching our stage is not closed. We keep finding new doors that might be the one, which is itself a quiet admission that we do not know which door, if any, is real. And that admission deserves a warning of its own, because there is a trap waiting for anyone who studies this list too eagerly. It is the temptation to look at whatever frightens our own civilization most in this particular decade and declare it the universal filter. A century ago, the obvious doom was a great war. A few decades ago, it was the bomb above all else. Today, many would point to runaway machines or a destabilized climate. Notice the pattern. The named filter keeps shifting to match the headline of the era, which should make us suspicious that we are not discovering the universal barrier at all, but simply projecting our present anxieties onto the whole galaxy. An alien species with a different biology, a different history, a different set of tools might face dangers we cannot even imagine and be entirely untroubled by the ones that keep us awake. So the disciplined version of the Great Filter does not say our specific fears are what silenced everyone else. It says only that the position on the staircase is deadly, not that anyone named Hazard is the killer. Holding that distinction is what separates honest reasoning from doom-mongering, and it is also, quietly, a small mercy because it means our particular nightmares are not necessarily our verdict. Step back from the list for a moment because the specific candidates matter less than the shape they all share. Self-destruction, engineered hazards, uncontrolled artificial intelligence, resource exhaustion, demographic decline, and there may be others we have not yet imagined. What unites them is not a common villain. It is a common position on the staircase. Every one of them strikes after a species becomes technological, and before it becomes durable and far-flung enough to be safe. They all live in the same narrow band, the one stretch of the climb we currently occupy. And this is the crucial clarity that separates the Great Filter from a tabloid prophecy. The hypothesis does not bet on any single one of these being the answer. It may be that none of them individually is the filter, and that the true barrier is simply the combined difficulty of surviving all of them at once. The way a swimmer who has finally reached deep water must contend not with one current but with cold, distance, and fatigue together. Any one survivable, all of them at once often not. The filter ahead, if it exists, could be one stage or several. It could be a danger we have named, or one we have not. The hypothesis does not pretend to know. It only insists that the silence implies that this stretch of the climb is where almost everyone falls. There is one more possibility on the upward stairs that deserves its own moment, because it does not require any catastrophe at all, and that makes it strangely harder to dismiss. It is simply the difficulty of becoming durable. Set aside wars and runaway machines and exhausted worlds. Even a wise, careful, fortunate civilization still faces the raw challenge of lasting long enough and spreading far enough to become genuinely visible across the galaxy, and to stay that way. The distances are staggering. The timescales required dwarf anything any human institution has ever sustained. A civilization would need to remain coherent, motivated and capable across spans of time so vast that languages, governments, and entire cultures would rise and fall many times within them. Perhaps the filter is not a cliff at all, but a marathon with no finish line in sight, a test of endurance so extreme that nearly everyone who starts it eventually stops. Not because they are destroyed, but because lasting that long and reaching that far is simply profoundly hard. In that version, the galaxy is silent, not because its civilizations died, but because almost none of them ever managed to become loud and durable enough to be heard. And now we arrive at the true center of the terror, the thing this entire journey has been circling, because the candidates, frightening as they are not the deepest fear. The deepest fear is the one we identified at the very beginning and have never been able to escape. The silence cannot tell us where the filter is. It is perfectly consistent with both readings, and the two readings are opposites. Recall the cruel logic one final time, now turn toward the future. If the early steps were genuinely improbable, if life and complexity and intelligence are rare, then the filter is behind us, and we are improbable survivors with open road ahead. But if the early steps are common, as the recent challenge to the hard steps model suggests they might be, then countless others reached our stage, and their absence means the filter took them after this point, which places it in front of us. And here is the part that turns the knife. Every discovery that pushes us toward the comforting belief that life is common, every independent microbe we might someday find on Mars or in a moon's hidden ocean, every second genesis, every confirmation that the lower stairs are easy to climb, simultaneously pushes the filter upward, toward our own future. The better the news about the prevalence of life, the worse the news about our prospects. We are trapped in a logic where the two things we most want to be true, that we are not alone and that we are not doomed, pull against each other. We cannot easily have both. And the silence, the one piece of evidence we possess in abundance, refuses to break the tie. Picture two galaxies. In the first, life almost never begins. Intelligence is vanishingly rare, and we are very nearly alone, the improbable winners of a barrier far below us. In the second, life ignites readily. Civilizations rise again and again, and nearly all of them fall at some step above the one we occupy. Now ask yourself what each of those galaxies sounds like to a telescope. The answer, the unbearable answer, is that they sound exactly the same. Both are silent. The galaxy where we are rare survivors and the galaxy where we are the next to fall produce the identical flat quiet. We hold in our hands a single fact, the absence of any voice but our own. And that fact has two meanings, one a story of extraordinary luck, and one a story of impending failure. And nothing in the fact itself tells us which story we are living inside. This is the moment to set the data down and simply feel where it has left us. Because some truths are not only measured, but inhabited. We are an exceedingly young species. The technology that lets us even ask this question has existed for a span so brief that, laid against the lifetime of the galaxy, it would vanish below any measure we tried to take of it. We woke up only a heartbeat ago, looked around a dark and silent room, and discovered that we cannot tell whether the room is empty because no one ever arrived, or empty because everyone who arrived is already gone. Both are possible. Both fit everything we see, and we have no way yet to choose between them. There is a particular kind of vertigo in that uncertainty, And it is worth naming honestly rather than dressing it up. It is the vertigo of not knowing your own position in a sequence whose later stages you cannot see. We do not know if the hardest thing this species will ever face is already behind us, accomplished by ancestors so distant they were not yet even animals, or whether it is in front of us, in some decision or invention or slow drift of the coming centuries. We do not know if we are the rare survivors or the next entry on a long list of the silenced, and we cannot resolve the question by wishing or by argument or by listening harder, because the listening gives the same answer either way. The not knowing is not a temporary gap in our data that better instruments will soon fill. It is, as far as we can currently tell, structural. The silence is built to be ambiguous, but I want to resist ending in pure dread, because dread is not actually where the honest reasoning leads, and to leave you there would be its own kind of distortion. Notice what the great filter does not say. It does not say that our destruction is certain. It does not say that we are doomed, or that the wall ahead is guaranteed, or that the silence is a verdict already passed. It says only that there is a barrier somewhere on the long climb, and that we do not know which side of it we are on. And if we do not know that the filter is ahead, then we also do not know that it is. The same uncertainty that denies us comfort also denies us despair. We might be the improbable survivors after all. The hardest stair might genuinely be far below us. The open road might be real. And there is something almost dignifying buried in the whole predicament. Something Carl Sagan understood when he looked at a photograph of our world reduced to a single pale point of light, and saw not insignificance, but responsibility. We are, as far as we can confirm, the only part of the universe currently asking where everyone is. Whatever else is uncertain, that much is real. For a stretch of cosmic history on at least one small world, matter has organized itself into something that can look at the silence, understand the silence, and be frightened by what the silence might mean. That is not nothing. If the filter is behind us, then we carry forward a flame that almost no one else ever lit. If the filter is ahead, then how we conduct ourselves on this fragile stretch of the climb, how carefully we handle the power that arrives before wisdom, may be the very thing that determines whether we become one more silence or the first lasting voice. In either case, the choices made by a young species standing on an uncertain stair are not trivial. They may be the only choices that matter. So this is where the journey leaves us. And I will not pretend it leaves us with an answer, because the truthful version of this story does not have one. The terrifying solution to the Fermi Paradox is not that aliens definitely destroyed themselves, and it is not proof that we are about to. The terrifying solution is quieter and far harder to live with than either. It is that the universe may be silent because the road from lifeless matter to a lasting, visible civilization passes through at least one barrier that almost nothing survives, and that the silence itself can never tell us whether humanity has already passed that impossible stage or has only just arrived in front of it. We are a species that has learned to read the sky, run the numbers, and pose the question, and the question stares back without blinking. The galaxy is silent. We do not know what that silence means for us, and we do not know, standing here on our small and fragile world, whether the hardest thing we will ever do is already finished, or whether it is still somewhere just ahead of us in the dark, waiting